Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video I am reading Aldehydes and Ketones. Introduction. Aldehydes and ketones are the first oxidation products of alcohols. Both these contain a carbonyl group and hence are collectively known as carbonyl compounds. In aldehydes, the carbonyl group is attached to one hydrogen atom and one alkyl or aryl group, while in ketones it is linked to either one alkyl and one aryl group or two alkyl or aryl groups, which may be same or different. The general formula of aldehydes and ketones are aldehydes and ketones. If two alkyl or aryl groups R and R dash are different, the ketone is said to be a mixed ketone, and if R and R dash represent the same alkyl or aryl group, the ketone is referred as a simple ketone. The functional group of aldehydes and is called the aldehydic group, while the functional group of ketones is called the ketonic group. Since both aldehydes and ketones contain the same carbonyl group, they have many similar chemical and physical properties. Nevertheless, aldehydes differ from ketones in many respects. They are more reactive towards nucleophilic addition reactions and also are easily oxidizable. This difference in behavior is mainly due to the presence of a hydrogen atom on the carbonyl group of aldehydes. Structure and nature of the carbonyl group. Structure of the carbonyl group. The C double bond in aldehydes and ketones, like the C double bond C, bond in alkanes is made up of one sigma bond and one pi bond. In the formation of carbonyl compound, C uses sp2 hybrid orbitals while O uses its atomic orbitals. According to the molecular orbital theory, one of the sp2 orbitals of carbon overlaps with a p orbital of oxygen group, forming CO sp2p sigma bond. The remaining two sp2 orbitals of the carbon atom form two additional sigma bonds, either by overlapping with 1s orbitals of two H atoms as in formaldehyde, or with 1s orbital of one hydrogen atom and one sp3 orbital of an alkyl group in aldehydes other than formaldehyde, or with two sp3 orbitals of two alkyl groups in ketones. All the three sigma bonds lies in the same plane and are inclined to one another at the angle of 120 degree. The two half-filled 2pz orbitals, one each on carbon and oxygen atom, overlap sideways to form a pi bond. The electron colored of the pi bond lies both above and below the CO bond pi bond. Look at the figure 4.1, structure of carbonyl group. From the above discussion, it is clear that the carbonyl carbon, oxygen and the two atoms directly bonded to the carbonyl carbon lie in one plane. This has been confirmed by electron diffraction and spectroscopic studies. Name of the carbonyl group. The oxygen atom in the carbonyl group is far more electronegative than carbon atom. As a result, the oxygen atom tends to attract the electron cloud of the pi bond towards itself. In other words, the pi electron cloud of is unsymmetrical. On the other hand, due to same electronegativity of the two carbon atoms, the pi electron of the bond is symmetrical. In other words, oxygen requires a small negative charge and carbon becomes slightly positively charged. Thus, the carbonyl group is polar in nature. Due to its polar nature, the carbonyl group is best represented as a resonance hybrid of the following two structures. The polar nature of the carbonyl group is supported by the fact that aldehydes and ketones have large dipole moments. Similarities between C double bond O and C double bond C bond. It may be pointed out here that the C double bond in aldehydes and ketones is similar to C double bond C bond in alkenes in many respects. Both are made up of one sigma bond and one pi bond. Both uses sp2 hybrid orbitals of the C atom for their formation. Both are planar in nature. Dissimilarities between C double bond O and C double bond C bond. Apart from the above similarities, bond differs from bond in the following respects. Carbon oxygen double bond is polar, but carbon carbon double bond is non-polar because of smaller size of oxygen as compared to carbon. C double bond O is shorter than that the C double bond C bond length. Carbonyl compounds undergo nucleophilic addition reactions, but compounds containing ethylenic double bond undergo electrophilic addition reaction. Nomenclature. Aldehydes in the common system. The names of aliphatic and aromatic aldehydes are obtained by the replacing the terminal from the name of the acid when they give upon oxidation by the suffix aldehyde in substituted aldehydes. The positions of the substituents are indicated by Greek letters alpha, beta, gamma, psi, with the carbon atoms next to the CHO group being designated as. In the UPSC system, aliphatic aldehydes are called alkanals, and the name of individual members are derived by replacing the terminal E from the name of the corresponding alkane by the suffix al. In substituted aldehydes, the parent carbon chain containing the aldehydic group is selected, and the positions of the substituents, if any, on the parent chain are indicated by numbers. The numbering of the parent chain in such a way that the aldehydic group, which is always present at the end of the chain, gets number as shown above. The common and IUPAC names of some simple aliphatic aldehydes are given below. Look at this table. When aldehyde group is attached to an alicyclic ring, the suffix carbaldehyde is added to the name of the hydrocarbon, for example 3-methyl cyclohexane carbaldehyde. The suffix carbaldehyde is also used when an unbranched carbon chain is linked to more than two aldehyde groups. In such cases, the compound is named as a derivative of the parent alkane, which does not include the carbon atoms of the functional groups. In all other cases, the suffix al is used and the carbon atoms of the functional groups are included in the parent alkane. An aromatic aldehyde, the CHO group is directly attached to the benzene ring. The simplest member of the family is called benzaldehyde. In case of substituted aromatic aldehydes, the positions of the substituents in the benzene ring with respect to the aldehyde group are indicated either by suffixes ortho, meta, and para, or by numbers 1, 2, 3, etc., with the carbon bearing the CHO group getting number 1. The name of a few aromatic aldehydes are given below: benzaldehyde, 2-hydroxybenzaldehyde, 2-methylbenzaldehyde, 3-methoxybenzaldehyde, 4-nitrobenzaldehyde, 4-methylbenzaldehyde. Ketones. In the common system, the names of the aliphatic and aromatic ketones are obtained by naming the two alkyl or aryl group in the alphabetical order attached to the keto group as two separate words and adding the suffix ketone when the two alkyl or the aryl groups are the same. The prefix di is attached to the name of the alkyl or the aryl group. Frequently, the aromatic ketones in which the carbonyl group is attached to the benzene ring are called phenols. In the IUPAC system, the ketones are called as alkanons. The name of the individual members are derived by replacing the terminal E from the nature of the corresponding alkane by the suffix 1. In substituted ketones, the parent chain containing the keto group is selected and the positions of the substituents, if any, indicated by numbers, the numbering of the chain being done in such a way that the keto group gets the lowest number. The common and IUPAC names of some aliphatic and alicyclic ketones are given below. Syntheses of aldehydes and ketones. Some important general methods of preparation of aldehydes and ketones are discussed below. Oxidation of alcohols. Aldehydes and ketones can be prepared by oxidation of alcohols. Aldehydes can be prepared by controlled oxidation of primary alcohols. The most commonly used oxidizing agent are acidified K2Cr2O7 and aqueous or alkaline KMnO4. However, when the alcohol has poor solubility in water, a solution of chromium trioxide and H2SO4 in acetone called Jones reagent is commonly used. Since all the oxidizing agents used are strong, therefore the aldehydes formed in the above processes are readily oxidized to carboxylic acids if allowed to remain in the reaction mixture. Further, since the boiling points of aldehydes are lower than those of corresponding primary alcohol, therefore aldehydes of low molecular mass can be easily distilled off as soon as they are formed. Mechanism of potassium dichromate oxidation of alcohols. Mechanism of oxidation of alcohol potassium dichromate occurs through initial formation of chromate ester Y, which loses a proton and HCrO3 ion to the form aldehyde. The proton loss may be either inter or intramolecular process, but in either case is reduced to Cr4 species. Special methods. The above method of preparing aldehydes by distillation of the aldehyde from the reaction mixture as soon as it is formed cannot be used for aldehydes having boiling points above 373 Kelvin. For such aldehydes, the following special methods are generally used. Collins reagent, Sarret's reagent is dipyridine chromium trioxide complex and is prepared by careful addition of CrO3 to excess of pyridine. Corey's reagent or pyridinium chlorochromate, abbreviated as PCC. It is prepared by mixing pyridine chromium trioxide and HCl in CH2Cl2. Pyridinium dichromate, abbreviated as PDC, is obtained by mixing pyridine, potassium dichromate and HCl in CH2Cl2. All these reagents are mild oxidizing agents. A solution of any of these reagents in CH2Cl2 is used for the oxidation of primary alcohols to aldehydes. Advantage of oxidation of alcohols by the above reagents. The advantage of these reagents over is that with these reagents, oxidation stops at the aldehyde stage, thereby preventing the further oxidation of aldehydes to carboxylic acids. The reason for selectivity in oxidation of these reagents in that these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrates, which are more easily oxidized than aldehydes themselves to the corresponding acids, as in evident from the following mechanism. Since in the absence of water, aldehyde hydrate cannot be formed, therefore further oxidation does not take place. However, in case of oxidation by acidic K2Cr2O7 or Jones reagent, water present in the reaction mixture converts initially formed aldehydes to aldehyde hydrates, which are readily oxidized. Oxidation of secondary alcohols. Ketones can be easily prepared by oxidation of secondary alcohols. The oxidation can be effected by a variety of reagents such as K2Cr2O7H2SO4, KMnO4H2SO4, Jones reagent, PCC, CH2Cl2. There is no danger of further oxidation of ketones since ketones are not easily oxidized. Open area oxidations. Secondary alcohol, saturated or unsaturated, can be conventionally oxidized ketones by open-air oxidation. It involves the treatment of a secondary alcohol with aluminium tertiary butoxide in presence of excess of acetone. When secondary alcohols get oxidized to ketone at the absence of acetone, which gets reduced to isopropyl alcohol. Mechanism. Open-air oxidation is just reverse of Mervin-Pondorf-Verlin reduction. It involves the transfer of an hydride ion through a six-membered cyclic transition state as shown below. Aldehydes are not satisfactorily prepared by open-air oxidation because the basic medium induces reaction between the aldehyde produced and the acetone used as hydride acceptor. Catalytic dehydrogenation of alcohols. Dehydrogenation means direct elimination of hydrogen. Dehydrogenation of alcohols is usually carried out by passing the vapors of alcohols over reduced copper at 573 Kelvin. Primary alcohols gives aldehyde, whereas secondary alcohols give ketones. The dehydrogenation process does not involve any risk of further oxidation of aldehyde to carboxylic acids from carboxylic acid. By reaction of carboxylic acids with alkyl or aryl lithium, both symmetrical and unsymmetrical ketones can be prepared in excellent yield by treatment of a carboxylic acid with excess of a suitable alkyl or aryl lithium in dry ether at 196 Kelvin, followed by acid hydrolysis of the addition product thus formed. By dry distillation of calcium salts of fatty acid. Distillation of calcium formate alone gives formaldehyde, while that of calcium salt of any other acid gives a ketone. This method is suitable only for the preparation of symmetrical ketones such as acetone, 3-pentanone, benzone, phenone, etc. Unsymmetrical ketones such as 2-butanone, 2-pentanone, etc. and aldehyde except formaldehyde cannot be prepared by this method. The reason being that when a mixture of two calcium salt is reacted, three products are formed. For example, dry distillation of a mixture of calcium formate and calcium acetate gives a mixture of formaldehyde, acetaldehyde, and acetone. If instead of calcium salts of monocarboxylic acids, calcium salts of dicarboxylic acids are used, this method can be used for the preparation of 5 and 6 membered cyclic ketones. By passing the vapors of fatty acids over manganese oxide at 573 Kelvin, this method is analogous to the above method. Formic acid alone gives formaldehyde. Acids other than formic acid gives ketone, whereas a mixture of formic acid and any other acid gives aldehydes other than formaldehyde. From acid chlorides. By Rosenmund reduction, for preparation of aldehydes only, acid chlorides are easily reduced to the corresponding aldehydes by passing hydrogen gas through boiling xylene solution of the acid chloride in presence of PD catalyst spotted over BaSO4 and partially poisoned by the addition of sulfur or quinoline. This reaction is called Rosenmund reduction. Formaldehyde cannot be prepared by this method since formal chloride is unstable at room temperature. Normally, aldehydes are further reduced to primary alcohols, but the addition of BaSO4 and sulfur poisons the palladium catalyst and thus does not permit the further reduction of aldehydes to alcohols. It may be noted here that LiAiH4 reduces acid chlorides to primary alcohols. However, lithium butoxyhydride is such a weaker reducing agent than LiAiH4 and hence it reduces acid chlorides to aldehydes. An advantage of this reagent is that it does not reduce other reducible groups present in the molecule. For example, acid chlorides needed for the purpose are themselves prepared by the action of thionyl chloride or phosphorus halides on carboxylic acids. Aldehydes can be obtained from carboxylic acid acid chlorides by the reaction with dialkyl cadmium for preparation of ketones only. Ketones can be easily prepared by the action of a suitable dialkyl cadmium compound on acid chlorides. Where R may be anyl, alkyl or aryl group, but R dash must be either a primary alkyl group or aryl group. The dialkyl cadmiums needed for the purpose are themselves prepared by the addition of anhydrous CdCl2 to suitable Grignard reagents. By reaction with lithium organocuprates for ketones only, lithium dialkyl cuprates react readily with acid chlorides to form ketones in excellent yields, where R and R dash may be alkyl or aryl groups. Lithium dialkyl cuprates needed for the purpose are themselves prepared by the action of cuprous halide on suitable alkyl or aryl lithium. Since acid chlorides are obtained from carboxylic acids, this reaction gives us yet another method for the preparation of ketones from carboxylic acids. Advantages: lithium dialkyl cuprates do not react with many of the functional groups with which Grignard reagents with organolithium do not react. Consequently, the presence of any one of these groups in the acid chloride does not interfere with the preparation of a ketone. For example, from nitriles by the reaction with Grignard reagents or organolithium compounds for ketones only. Grignard reagents or organolithium compounds add to alkyl or aryl nitrides to form addition product which upon subsequent acid hydrolysis give ketones. Instead of allyl or aryl nitrides, hydrocyanic acid is used in the above reaction. Aldehydes are produced. From 1,3-dithiene, one of the most recent methods for the synthesis of aldehydes and ketones is by the use of 1,3-dithiene. 1,3-dithiene or 1,3-dithicyclohexene is an alicyclic hydrocyclic compound and is prepared by the action of formaldehyde with 1,3-propane dithiol in presence of trace of an acid. 1,3-dithiene is a weak protonoic acid and thus can be converted into its anion by treatment with a strong base such as N-butyl lithium. The resulting carbanion is stabilized by two sulfur atoms because they are easily polarized. Synthesis of aldehydes. The 1,3-dithiene carbanion acts as a strong nucleophile and reacts with an alkyl halide by SN2 mechanism to form alkyl derivatives of 1,3-dithiene. This upon subsequent hydrolysis with HgCl2 either in methanol or aqueous acetonitrile gives the corresponding aldehyde. The complete sequence of reaction is depicted below. Synthesis of ketones. Ketones can be easily prepared from 1,3-dithiene by first converting it into its disubstituted derivative in two stages followed by hydrolysis with HgCl2 in aqueous methanol. An aldehyde can be converted into a ketone by first making its thioacetal with 1,3-propan-dithiol. This upon alkylation with a suitable alkyl halide in presence of N-bule gives a thioketal which upon hydrolysis with HgCl2 in aqueous methanol gives the corresponding ketone. From alkenes. Alkenes react with ozone to form ozonoids which upon subsequent cleavage with Jaden dust affords aldehydes ketones. Under these conditions, ethylene gives formaldehyde. Symmetrically, disubstituted alkenes give other aldehydes while tetrasubstituted alkenes give ketones. From alkynes. By hydration of alkynes, hydration of mono or disubstituted alkynes with dilute H2SO4 of HgSO4 at 333 Kelvin mainly gives methyl ketones acetylene. Under these conditions, form acetaldehyde. By hydroboration oxidation of alkynes. Aldehydes and ketones can be also prepared by hydroboration oxidation of alkynes, whereas symmetrical non-terminal alkynes give a sign ketone, unsymmetrical non-terminal alkynes gives a mixture of both possible ketones in which the methyl ketones predominates. Aldehydes can likewise be prepared from terminal alkynes, but to avoid complications due to double addition of diborane, bulky sterically hindered boranes such as bis 1,2-dimethylpropyl borane, commonly known as dicyclohexane, Mylborane is used to plane of B2H6. From acid to acetic ester, methyl ketones can be conventionally prepared by alkylation of ethyl acetoacetate, commonly known as acetoacetic ester. The process involves the conversion of acetoacetic ester into its sodium salt by treatment with sodium ethoxide. This is followed by alkylation with a suitable alkyl halide. When alkyl acetic ester is obtained, ketonic hydrolysis of the alkyl acetoacetic ester obtained with dilute aqueous AQH followed by acidification gives a beta ketoacid, which upon heating undergoes decarboxylation to give the methyl ketone. For example, some special methods for synthesis of aromatic aldehydes and ketones. Aromatic aldehydes and ketones are generally prepared by the following methods, which are however not applicable to aliphatic series. Oxidation of methyl benzenes. Aromatic aldehydes can be prepared by the oxidation of methyl benzene with chromium trioxide in acetic anhydride. The gem diacetate first formed is isolated and hydrolyzed with dilute H2SO4 HCl to yield the corresponding aromatic aldehyde. For example, Itard reaction. Methyl benzenes can also be oxidized to aldehydes with a solution of chromyl chloride. The brown complex thus precipitated is separated and decomposed with water to give the corresponding aldehyde. This reaction is called Itard reaction. Reimer-Tiemann reaction. This is a convenient method for the preparation of ortho-hydroxybenzaldehydes. In the reaction, a phenol is heated with chloroform and alkali at 333 Kelvin to 343 Kelvin. When an ortho-hydroxybenzaldehyde along with a small amount of the P isomer is formed, for example, this reaction is called Reimer-Tiemann reaction. Friedel-Crafts reaction. This is one of the most convenient and widely used method for the preparation of aromatic ketones in which the ketonic group is directly attached to at least one aromatic ring. It involves the treatment of an aromatic hydrocarbon with an acid halide in the presence of a Lewis acid such as anhydrous aluminum chloride. Getterman-Koch aldehyde synthesis and Getterman formylation. Benzaldehyde and many other aldehydes can be conveniently prepared by treating benzene or any other aromatic hydrocarbon with a mixture of carbon monoxide and HCl in presence of a catalyst consisting of anhydrous aluminum chloride and a trace of cuprous chloride. The electrophilic attack of the carbon on the benzene ring first gives a alpha complex which subsequently loses a proton to form the aldehyde. If CO in the above reaction is replaced by HCN, the reaction is called Getterman aldehyde synthesis or Getterman formylation or simply Getterman synthesis. This reaction has been already discussed in details in Unit 2. Physical properties of aldehydes and ketones. Physical state and smell. Formaldehyde is a gas at room temperature while other aliphatic aldehydes and ketones up to C11 are colorless mobile liquids and the still higher members are solids. Aromatic aldehydes and ketones are liquids, but some of them, such as p-hydroxybenzaldehyde, vanillin, benzophenone, etc., are solid at room temperature. Lower aldehyde possesses an unpleasant pungent odor, while highly members have a fruity smell. Ketones, on the other hand, generally possess a pleasant smell. Boiling points. The boiling points of aldehydes and ketones are somewhat higher than non-polar compounds and weakly polar compounds of comparable molecular masses. This is due to the reason that these aldehydes and ketones contain polar carbonyl groups and undergo intermolecular association due to dipole-dipole interaction between the opposite ends of the dipoles. Among isomeric aldehydes and ketones, ketones have slightly higher boiling point. This is due to the presence of two electron donating alkyl groups around the C-double bond O group, which makes them more polar, for example. These dipole interactions are however weaker than intermolecular H bonding between molecules. Consequently, the boiling point of carbonyl compound are much lower than those corresponding alcohols and carboxylic acid. Melting point of aldehyde and ketone, however, do not show regular with increasing molecular mass. Solubility. Lower aldehydes and ketones containing up to 4 carbon atoms such as methanol, ethanol, propanol, etc. are soluble in water due to H bonding between the polar carbonyl and the water molecules. But the solubility rapidly falls off as the size of the alkyl group increases. With increasing molecular mass, as a result, the higher members insoluble in water. Similarly, the solubility of aromatic aldehydes in ketone is much lower than their corresponding aliphatic analogues because of the larger hydrocarbon part present in their molecules. However, all aldehydes and ketones are fairly soluble in organic solvents. Nature of chemical reactions of aldehydes and ketones. The chemical reactions of aldehydes and ketones are mainly due to the polarity of the acidity of the alpha hydrogen atom. Polarity of the carbonyl group and mechanism of nucleophilic addition reactions. Due to greater electronegativity of oxygen carbon in aldehydes and ketone is quite polar. The carbonyl carbon bears a partial positive charge and it electron deficient while the oxygen atom carries a partial negative charge and hence is electron rich. Now What type of reagents are expected to attack the carbonyl group? Since the carbon atom is electron deficient and it is electrophilic and hence can be readily attacked by the bases or nucleophiles. Conversely, the oxygen atom being electron with a nucleophilic and hence can be attacked by acids and electrophiles. Let us first consider the nucleophilic attack on the carbonyl atom carbon. As the nucleophilic attacks the carbon atom of the carbonyl group, the hybridization of carbon changes from sp2 to sp3 and a new bond is formed between the carbon atom and the nucleophile. The pi electrons of the C double bond O are completely transferred to the oxygen atom, giving a tetrahedral intermediate which subsequently picks up a proton either from the solvent or from the reagent to give the addition product. The overall reaction thus involves the addition of a nucleophilic to the electron deficient carbon and a proton to electron oxygen atom of the carbonyl group. Such type of reactions are called nucleophilic addition reactions, are typical of aldehydes and ketones. Role of acid catalysis in nucleophile addition reaction. Let us now consider the electrophilic attack on oxygen atom. In presence acids, the oxygen atom of the carbonyl groups get protonated due to protonation oxygen atoms, a positive charge which in turn pulls the electron of the pi bond more strongly towards itself. As a result, the positive charge on the carbon atom increases and the nucleophile attack is facilitated. It is because of this increase in electron deficiency or the electrophilicity of the carbonyl group carbon in presence of acid that even weak nucleophiles such as water alcohols, thioalcohols, amines, etc. can attack the carbonyl group readily. In the light of the above discussion, the reactions of the carbonyl group may be regarded either as nucleophilic addition or electrophilic addition reactions, but we usually classify them as nucleophilic addition reaction because of the following three reasons. The attack of the nucleophile on carbonyl carbon involves the formation of a new carbon nucleophile bonds and it is rate determining step of the reaction. The ability of the electronegative oxygen atom to accommodate the negative charge facilitates the nucleophile attack or carbon. The addition of electrophile to the carbonyl oxygen is a reversible reaction in which the equilibrium lies far to the side of reactants. As a result, the sub can only catalyze rather than initiating the nucleophiling attack. Nucleophilic addition reactions under basic conditions. Some nucleophilic additions such as carbon cyanohydrin formation addition of organometallic and Grignard reagents occur under basic conditions. In these reactions, the nucleophile first attacks the carbon group, giving the tetrahedral intermediate, which then accepts a proton on treatment with water or the acid. From the above discussion, it follows that the nucleophilic addition reactions of aldehydes and ketones occur under both acidic and basic conditions, whereas the reaction of weak nucleophiles occur under acidic conditions. Those of strong nucleophiles occur under basic condition. The major difference between these two mechanisms. Electronic factors. The reactivity of aliphatic aldehydes and ketones can also be explained in terms of electronic factors. The alkyl groups release electrons and thus destabilize the transition state by intensifying the negative charge on the carbonyl oxygen. Since aliphatic aldehydes contain one alkyl group and aliphatic ketones contain two such groups, therefore destabilization of the transition state resulting from a ketone would be much greater than the resulting from aldehyde. Thus, aliphatic aldehydes are more reactive than aliphatic ketones. Further, since formaldehyde does not have any alkyl group, the resulting transition state would be more stable and hence formaldehyde is the most reactive of all the simple aliphatic aldehydes and ketones. Alternatively, the relative reactivity of aldehydes and ketones can also be explained as follows. Aliphatic aldehydes and ketones. The ease with which with a nucleophile attacks the carbonyl carbon depends upon its electron deficiency. Magnitude of the positive charge. Evidently, greater the electron deficiency, more facile is the nucleophilic attack and hence more reactive is the carbonyl compound. Now, as we go from the two H atoms of the formaldehyde and successively replaced by methyl group. Since methyl group is in an electron donating group, it tends to reduce the magnitude of the positive charge by its plus I effect. As a result, the electron deficiency of the carbonyl carbon and hence the reactivity of aldehydes and ketones decreases in the following order. In contrast, electron withdrawing substituents, halogens, etc., when present on the alkyl groups reactively chase the reactivity of carbonyl compound in these addition reactions. For example, aromatic aldehydes and ketones. In general, aromatic aldehydes and ketones are less reactive than the corresponding aliphatic analogues. This is due to the reason that the electron donating resonance effect of the benzene ring increases the electron density on the carbonyl carbon, thereby repelling the nucleophiles. As a result, aromatic aldehydes and ketones are less reactive than the corresponding aliphatic aldehydes and ketones. However, amongst aromatic aldehydes and ketones, aromatic aldehydes are more reactive than aryl ketones, which in turn are more reactive than diaryl ketones. Further, electron withdrawing substituents, when present in the benzene ring at ortho and para position, greatly enhance the reactivity in electron donating groups, greatly reduce the reactivity of the carbonyl compound towards nucleophile addition reactions. Thus, nucleophilic addition reactions of aldehydes and ketones. Aldehydes and ketones give two types of nucleophilic addition reaction. These are simple without elimination nucleophilic addition reaction, nucleophilic addition reactions followed by elimination. Simple without elimination nucleophilic additions. Some important simple nucleophilic addition reactions are discussed below. Addition of sodium bisulfate. Most of the aliphatic aldehydes and methyl ketones which are not sterically hindered react with a saturated solution of sodium bisulfite to form crystalline solids called sodium bisulfite addition compounds. Amongst aromatic aldehydes and ketones, only benzaldehyde form a sodium bisulfite addition compound. Testophenone does not. It may be noted here that although it is a reversible reaction, yet the use of a saturated solution of NaHSO3 shifts the equilibrium towards right and the addition product gets precipitated. Ketones containing bulky alkyl groups such as diethyl ketone, diisopropyl ketones, methyl tertiary butyl ketone, and ditertiary butyl ketone do not react with NaHSO3 due to steric hindrance. It involves the nucleophilic attack of the bisulfite ion on the carbonyl carbon followed by proton transfer. The driving force for proton transfer from I to second is the resonance stabilization of resultant anion. Important. These bisulfite addition compounds are usually crystalline solids. When heated with dilute mineral acid or aqueous alkalis, these products decompose to regenerate the original aldehyde or the ketone. Therefore, this reaction is used in the purification and separation of aldehydes and ketones from non-carbonyl compounds. Addition of hydrogen cyanide. Both aldehydes and ketones add a molecule of hydrogen cyanide to form cyanohydrins. The reaction is usually carried out in presence of a base which react with HCN to give Cn negative ion. Being a strong nucleophile readily adds to the CO group. Since HCN is a poisonous gas, the reaction is usually carried out by treating the carbonyl with an aqueous solution of NaCN or KCN and acidifying the solution by adding mineral acid till the cyanide solution drops from pH 12 to 13 due to hydrolysis of NaCN. Mechanism. The reaction involves the nucleophilic attack by the cyanide ion to form, which subsequently accepts a proton from H2O to yield the cyanohydrin. Synthetic importance. Cyanohydrin are important synthetic substances since they can be hydrolyzed to give alpha hydroxy acids. Addition of Grignard reagents. Organolithium and organozinc compounds. Grignard reagents and organolithium compounds are strong nucleophiles. They add readily to aldehydes and ketones. Addition product which upon subsequent hydrolysis with dilute mineral acids from alcohols. The type of alcohol formed depends upon the aldehyde or the ketone used. For example, formaldehyde gives primary alcohol, other aldehyde gives secondary alcohol, while ketones yield tertiary alcohols. Reformotsky reaction. It involves the reaction between an aldehyde or a ketone with the alpha bromoester in presence of metallic zinc to give an addition product, which upon acidification to gives beta hydroxy ester. Mechanism of Reformotsky reaction is similar to Grignard reaction. Zinc is used in place of magnesium since the organo-zinc compounds are less reactive than Grignard reagent and hence do not react with esters but are still reactive enough to react with aldehydes and ketones. The alpha bromoester first reacts with zinc to form an organo-zinc compound which then adds to the C double bond O group of the aldehyde or the ketone. Addition of alcohols. Aldehydes react with alcohol in presence of dry HCl gas to form gem dialkoxy compound known as acetals. A hemiacetal is first formed by the addition of one molecule of an alcohol to the carbonyl group. In being unstable, immediately react with another molecule of alcohol to form stable acetals. Dry HCl gas absorbs the water produced in these reactions and shifts the equilibrium in the forward direction. If instead of two molecules of a monohydric alcohol, one molecule of dihydric alcohol such as ethylene glycol is used, a cyclic acetal is formed. In actual practice, a mixture of an aldehyde with excess of ethylene glycol is reflexed in presence of p-toluene sulfonic acid. Ketones, however, do not react with monohydric alcohols but do so with dihydric alcohols to give cyclic ketones. Mechanism: the formation of acetals or ketones is catalyzed by acid and is believed to occur by the following steps. Uses of acetyl ketones as protecting groups. Acetals and ketones, like other ethers, are stable towards bases and nucleophiles under neutral or basic conditions but are hydrolyzed back to aldehydes and ketones respectively upon treatment with aqueous mineral acids. The easy conversion of aldehydes and ketone is the corresponding acetals and ketones under anhydrous acid conditions, and thus that of acetals and ketones to parent aldehydes and ketones respectively acidic conditions make acetals and ketones as valuable protecting groups for carbonyl compound. Example: suppose we want to prepare 5-hydroxy 2-pentanone by LiAiH4 reduction of ethyl 4-exopentane. Direct reduction is not possible since it will reduce the carbonyl group as well. Therefore, the keto gives first directed by ketalization and the ester is then reduced. Subsequent hydrolysis of the desired compound. Nucleophilic addition reactions followed by elimination of a molecule of water. Reaction with ammonium derivatives. Aldehydes and ketones undergo nucleophilic reaction with a number of ammonium derivatives such as hydroxyamine, hydrazine, phenylhydrazine, 2,4-dinitrophenylhydrazine, and semi-carbazide in acidic medium to form acidation products with automatically lose a molecule of water to form containing C-double bond N group. These reactions are also called addition, elimination reaction, or condensation reaction. If we represent the ammonium derivative by NH2G, where formation of the final product may be depicted as under. The reaction is reversible and is catalyzed or by acids. The equilibrium favors the product due to rapid dehydration of the initial form tetrahedral addition product. The names and the structures of the product with some ammonium derivatives are given below. The ammonium derivatives used as nucleophilic reagent in these reactions are usually employed in form of their salts, such as hydroxyamine, hydrochloride, hydrazine sulfate, phenylhydrazine, hydrochloride, semi-carbazide, hydrochloride, etc. The free nucleophiles are generated from these salts by carrying out the reaction in presence of sodium acetate. It may be noted here that the ammonium derivatives such as phenylhydrazine, semi-carbazide, etc., which contain 2 or more non-equivalent nitrogen atoms. Only the nitrogen atom which is more nucleophile will initiate the nucleophilic attack on the carbonyl group. For example, in C6H5NHNH2, the nitrogen which is attached to the benzene ring is less nucleophile because of its lone pair of electrons is delocalized on the benzene ring. Therefore, the other nitrogen is involved in the reaction. Similarly, in NH2CONHNH2, the 2 nitrogen atoms adjacent to the carbonyl group are less nucleophilic because their lone pairs of electrons are delocalized over C-double bond O group. As a result, the NH2 group further away from the carbonyl group takes part in the condensation reaction. Control of pH during addition of ammonium derivatives to aldehydes and ketone. The addition of ammonium derivatives to aldehydes and ketone is catalyzed by acids. In acidic medium, the oxygen of carbonyl groups get protonated, which in turn by resonance increases the positive charge on the carbonyl carbon. As a result, weak and nucleophiles like ammonium derivatives really attack the carbonyl group. In case the medium is too acidic, the ammonium derivatives, being basic in nature, will form their respective ammonium salt due to the absence of a lone pair of electrons on the nitrogen atom. These ammonium salt will no longer be nucleophile and hence the reaction will occur. Therefore, to carry out such reactions, an optimum value of pH is needed. Usually, a pH of around 3.5 is employed. Further, these derivatives can be decomposed by boiling with dilute mineral acid to regenerate the original carbonyl compound. Therefore, these derivatives are also used for the purification of aldehydes and ketones. The reaction of aldehyde and ketone with the ammonium derivatives are given below. Reaction with ammonia. Most of the aliphatic aldehyde except formaldehyde react with ammonia to form addition product called aldehyde ammonous. These products are unstable and immediately loses a molecule of water to form aldimines, which subsequently undergo polarization. For example, formaldehyde react differently to form hexamethyl amine, which is used as urinary antiseptic under the name urotropine. Nitration of hexamethyl tetraamine under controlled condition gives the well-known explosive RDX. Unlike aliphatic aldehydes and benzaldehyde react with ammonia to form a complex product called hydrobenzoamide. Rest of aliphatic ketones, however, give complex condensation product with ammonia. For example, acetone reacts with ammonia to give diacetone amine. Condensation reactions of aldehydes and ketone. Reaction in which two or more molecules of the same or different reactants combine with or without the loss of small molecules such as water, ammonia, alcohol, etc. are called condensation reactions. Some important condensation reactions of aldehydes and ketones are discussed below. Aldol condensation, as important reaction based on the acidity of alpha hydrogen aldehydes ketones in is called condensation, which can be carried out either under acidic or basic conditions. Base catalyst aldol condensation, two molecules of an aldehyde or a ketone having alpha hydrogen condense in presence of a dilute alkali to form beta hydroxy benzaldehyde or beta hydroxy ketone. These beta hydroxyhides or hydroxyketones are collectively called aldols, and the reaction is called aldol condensation. Mechanism. The aldol condensation occurs through the following three equilibrium steps. In the first step, the base OH ion abstract one of three acidic alpha hydrogen to form carbanion or the enolate ion, which is stabilized by resonance. The carbanion or the enolate ion, being a strong nucleophile, attacks the carbonyl group second molecule of acetaldehyde to form the anion. The anion finally abstracts a hydrogen from water to form aldol. Dehydration of aldols. The products of aldol condensation, when heated with dilute acids, undergo dehydration, leading to the formation of alpha beta unsaturated aldehydes or ketones. For example, mechanism. In presence of acids, the aldol gets protonated, which then loses a proton and a molecule of water to give the corresponding alpha beta unsaturated aldehydes or the ketone. However, if the dehydration of an aldol produces a double bond in conjugation with the benzene ring, then the aldol condensation of such aldehydes or ketones does not give aldol as the final product, but instead the corresponding alpha beta unsaturated carbonyl compound is always obtained. For example, limitations. Only aldehydes and ketones which contain at least one alpha hydrogen undergo aldol condensation. Thus, compounds like formaldehyde, trimethylacetaldehyde, aromatic aldehydes, benzaldehyde, toldehyde, ansaldehyde, diaryl ketones, which do not contain alpha hydrogens, do not undergo aldol condensation. Aldols still contain one or more acidic alpha hydrogen atoms, therefore, they can undergo further aldol condensation to give complex resinous products. This happens particularly when a strong alkali is used to induce a aldol condensation. Acid catalyst aldol condensation. Aldol condensation can also be induced by acids. However, in such cases, aldols are not the final products. Instead, they readily undergo dehydration to give alpha beta unsaturated aldehydes or ketones. Methyl oxide still contains alpha hydrogens, therefore, it undergoes further aldol condensation to yield ultimately furon. Mechanism. The acid catalyst aldol condensation occurs through the following steps. In presence of acids, the aldehyde or the ketone is partially converted into its anol. The anol I thus formed act as a nucleophile and adds to the protonated group of another molecule of acetone to give a duct, which subsequently loses a proton to give the aldol, diacetone alcohol. Diacetone alcohol then undergo acid catalyst dehydration to give methyl oxide. Crossed aldol condensation. Aldol condensation is not confined to the condensation of two molecules of the same aldehyde or ketone, self condensation. It can also take place between two different aldehydes or ketones or between one aldehyde and one ketone. Such an aldol condensation between two different aldehydes or two ketones or between one aldehyde and one ketone is called mixed aldol condensation or crossed or mixed aldol condensation. In principle, such condensations can give a mixture of four products which are difficult to separate. Therefore, crossed aldol condensation are of little synthetic value. However, if one of the carbonyl compound does not possesses alpha hydrogens, example formaldehyde, benzaldehyde, etc., then cross aldol condensations are of great synthetic utility as discussed below. With formaldehyde with benzaldehyde, the initially formed aldol undergo dehydration to form an alpha beta unsaturated carbonyl compound. The driving force for this dehydration is the conjugation of the double bond with the benzene ring and the carbonyl group. If benzaldehyde is used in excess, the initially formed benzyl acetone further condenses with another molecule of benzaldehyde to form dibenzyl acetone. Such a base catalyst cross aldol condensation between an aromatic aldehyde and an aliphatic aldehyde or a ketone is called Claisen-Suchmet condensation or simply Claisen reaction. Even aliphatic esters containing alpha hydrogen atoms undergo Claisen-Suchmet condensation on treatment with an aromatic aldehyde in presence of base, for example. Even aliphatic esters containing alpha hydrogen atoms undergo Claisen-Suchmet condensation on treatment with an aromatic aldehyde in presence of a base. Mechanism of Claisen-Suchmet reaction is similar to that of base catalyst aldol condensation. Here the aliphatic aldehyde or the ketone which contains alpha hydrogen forms the carbanion which subsequently adds to the C double bond O group of the aromatic aldehyde to form the anion I, which then picks up a proton from H2O to form aldol second. The aldol subsequently undergo base catalyst dehydration to give the corresponding alpha beta unsaturated compounds. Benzoin condensation. Aromatic aldehydes which do not contain alpha hydrogen atoms cannot undergo aldol condensation. However, in presence of alcoholic potassium cyanide, they undergo self-condensation in a different manner to form alpha hydroxy ketones commonly called benzoins, after the name of the product obtained from benzaldehyde, and the reaction is called benzoin condensation. Mechanism. Ketones of the reaction shows that benzoin condensation in first order in cyanide ion and second order in benzaldehyde. Step 1. The cyanide ion being a strong nucleophile adds to the C double bond O group of benzaldehyde to form anion I, which being unstable undergo a proton transfer to carbanion second. The driving force for this proton transfer is the resonance stabilization of the resulting anion second. The carbanion second subsequently adds to the C double bond O group of another benzaldehyde molecule to give the addition product 3. This addition product then undergoes another proton transfer to afford anion 4, which subsequently eliminates cyanide ion to form benzoin. The driving force for the proton transfer from anion 3 to anion 4 is the ability of the anion 4 to eject cyanide ion, which is a good leaving group. Specific action of cyanide ion. It may be noted here that benzoin condensation is specifically catalyzed by Cn negative ion and not by OH negative ion. This specificity is due to the following reason. The cyanide ion is a strong nucleophile and hence readily attacks the carbonyl compound. Cyanide ion can stabilize the carbon ion to which it is attached by resonance. Cyanide ion is a good leaving group and hence can easily depart after the reaction. Perkin condensation. Perkin condensation is also closely related to Claisen-Suchmet reaction. It involves the reaction of an aromatic aldehyde with an aliphatic anhydride in presence of sodium salt of the carboxylic acid from which the anhydride has been derived as the base to first form a condensation product which upon hydrolysis gives the corresponding alpha beta saturated acid, for example benzaldehyde. When heated with acetic anhydride in presence of sodium acetate at 453 Kelvin gives a condensation product which upon hydrolysis gives cinnamic acid. The alpha hydrogen atoms of acid anhydrides, like those of aldehydes and ketones, are weakly acidic. The sodium salt of the carboxylic acids act as the base and abstracts the alpha hydrogen of the acid anhydride to form a carbanion. The carbanion then adds to the carbonyl group of the aromatic aldehyde to give an anion I first, which accepts a proton from the acid to form the aldol second. Under the basic conditions of the reaction, the aldol thus formed undergo dehydration to yield the condensation product third, which upon subsequent hydrolysis gives the alpha beta and saturated acid as shown below. Novengal condensation. It is closely related to base catalyst aldol condensation. It involves the condensation of an aliphatic aromatic aldehyde with an active methylene compound such as malonic acid, malonic ester, cyanoacetic ester, acetoacetic ester, nitroalkanes, etc. in presence of a base such as pyridine or piperidine to form alpha beta unsaturated compounds. Ketones do not undergo Novengal condensation with malonic acid or malonic ester but do so with cyanoacetic ester, which contains more acidic alpha hydrogen atoms. Manish reaction. It involves the reaction between an active methylene compound, usually an analyzable ketone, formaldehyde and an amine, usually a secondary amine, in presence of an acid to give a product which upon basification yields a beta aminocarbonyl compound commonly known as Manish base, for example. It is a very general reaction and it is used for introducing one carbon atom into the analyzable ketone. Although the reaction is usually carried out under acidic medium, but neutral and basic medium have also been used. Structural residuosides of reactants. Base sides, analyzable ketones, beta ketoesters, beta cyanoesters, nitroalkanes and terminal alkynes have also been used in Manish reaction. Although formaldehyde is the most commonly used aldehyde, but higher aldehydes have also been used. Similarly, besides secondary amines and primary amines and ammonia have also been used, resulting in 2 and 3 successive alkylation reactions respectively. Mechanism. First of all, the amine reacts with formaldehyde in presence of an acid to give an iminium salt, which subsequently eliminates a molecule of water to form an electrophile. Haloform reaction. Methyl ketones can be easily oxidized to carboxylic acids with one carbon atom less than the parent ketone with a halogen in presence of a base hypohalides. Since a haloform is one of the products of the reaction, it is generally known as haloform reaction. Mechanism. Haloform reaction is believed to occur by the following two stages: base protonated halogenation of ketones, cleavage of carbon-carbon bond. The trihaloketone formed above is not stable under alkaline conditions of the reaction and hence reacts further to produce a haloform and the salt of a carboxylic acid. Iodoform test. Iodoform test is a haloform reaction using iodine as the halogen. Chloroform and bromoform are liquids and hence are difficult to characterize. However, iodoform is a yellow colored solid with a sharp melting point 392 Kelvin and hence can be easily characterized. It is because of this reason that iodoform test is used as diagnostic test for the presence of COCH3 grouping in any organic compound. When such a compound is treated with I2NaOH, a yellow pipette of CHI3 is formed. From methyl ketones, iodoform test is also given by all methyl carbonyls when are oxidized by the halogen I2 present in the reaction mixture to the corresponding methyl ketones. Acetaldehyde CH3CH2 is the only aldehyde and ethanol is the only primary alcohol which also gives iodoform test Baeyer-Villiger oxidation. It involves the conversion of a cyclic ketone into esters and cyclic ketones into lactones by treatment with a per acid such as perbenzoic acid, metachloroperbenzoic acid, acid trifluoroparasitic acid. Of all the para acids, trifluoroparasitic acid is the most reactive because trifluoroacetate ion is a very good leaving group. The reaction is catalyzed by acids and involves the nucleophilic addition of per acid, the carboxyl carbon of the ketone. The key step of this reaction is the migration of group R from carbon electron deficient oxygen as shown below. Most probably, the two steps involving the 1,2 migration of group R and loss of carboxylate ion concentrated occur simultaneously as shown below. Evidence in favor of the mechanism. The above mechanism is supported by the observation that labeled carbonyl oxygen atom of the ketone becomes the carbonyl oxygen atom of the ester. Migratory aptitude of various groups. In case of unsymmetrical ketones, the group that migrates is R, which can more easily supply the electrons. The tendency of the groups to migrate, commonly called migratory aptitude from carbon to electron deficient oxygens, follows the order. Among sterile groups, the order is p-methoxyphenyl, p-toluyl phenyl, p-chlorophenyl. The product actually formed during Baeyer-Villiger oxidation depends upon the migratory aptitude of groups. For example, the oxidation of acetophenone with perbenzoic acid gives phenyl acetate and not methyl benzoate because phenyl group has a greater tendency to migrate to electron deficient oxygen than methyl group. Similarly, Baeyer-Villiger oxidation of pinacoline gives tersh-butyl acetate and not methyl tersh-butyl acetate and not methyl pivalate because migratory aptitude for tersh-butyl group is greater than that of methyl group. Reduction of aldehydes and ketones. Aldehydes and ketones can be easily reduced to form various products depending upon the nature of the reducing agent used as discussed below. Reduction to alcohols. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols either catalytically with H2 in presence of Ra, NiPT, PD or Ru or chemically by lithium aluminium hydride and sodium borohydride. Since the hydrogenation of carbon-carbon double bond is much easier than carbonyl group, catalytic hydrogenation of alpha beta unsaturated aldehydes or ketones give the corresponding saturated alcohols. NaBH4 is a milder reducing agent than LiAiH4 and is used in a variety of solvents such as water, alcohols, etc. On the other hand, LiAiH4 is a powerful reducing agent. It is highly sensitive moisture and hence is used in only anhydrous aprotic solvents such as either tetrahydrofuran, dioxane, etc. For reduction of aldehydes and ketones, NaBH4 is preferred to LiAiH4 since it is more convenient to use because of its lack of reactivity towards water. Neither NaBH4 or nor LiAiH4 reduce isolated double bonds. However, in case of alpha beta unsaturated aldehydes or ketones, LiAiH4 reduces only the C double bond O group, but NaBH4 reduces both the C double bond O and C double bond C, giving a mixture of products in which the C double bond O reduction product, single reduction product, predominates over the double reduction product of both the C double bond O and C double bond C groups. Thus, the mechanism of NaBH4 or LiAiH4 reduces has already been discussed in Unit 1. Marvin-Pondorf-Verlin reduction. It is mainly used for reduction of ketones since aldehydes under the basic conditions of the reaction may undergo polymerization reactions. It is the reverse of Opnier oxidation and is carried out by heating a ketone with aluminum isopropoxide in presence of excess of isopropyl alcohol. During this reaction, the ketone is reduced to the corresponding alcohol at the expense of isopropyl alcohol, which is oxidized to acetone. Since acetone is the lowest boiling constituent of the mixture, it is distilled off continuously so as to displace the equilibrium in the forward direction. MPV reduction is a highly selective method and does not attack the double bond. It is therefore a useful method for the reduction of unsaturated carbonyl compounds to the saturated alcohols. Mechanism. The mechanism of this reaction has already been discussed in Unit I. Reduction to hydrocarbons. The carbonyl group in aldehydes and ketones can be reduced to methylene group to form hydrocarbons. The following methods are generally used. Clemmensen reduction. This involves the reduction of an aldehyde or a ketone with a zinc amalgam and concentrated hydrochloric acid, for example. Clemmensen reduction works well for ketones but not for aldehydes. It is widely used for reduction of such ketones which are sensitive to alkalis. Clemmensen reduction is believed to occur by the following mechanism. In this method, the aldehyde or ketone is heated with hydrazine and a strong base such as KOH or potassium tetrohydroxide in a high boiling liquid solvent such as ethylene glycol at 453 to 473 Kelvin to give the corresponding hydrocarbon. Wald-Kirschner reduction is particularly useful for reduction of acid-sensitive aldehydes or ketones. Mechanism. This reduction is believed to occur through intermediate formation of hydrazone of the aldehyde or ketone which subsequently decomposes under the basic conditions of the reaction to form the corresponding hydrocarbon with evolution N2 gas according to the following mechanism. Synthetic importance. Both Clemens and Wolff-Kishner reductions are widely used for the synthetic of alkyl benzenes containing straight chains which are otherwise difficult to prepare by direct Friedel alkylation reactions. For example, FC reaction of benzene with isobutyl chloride does not give isobutyl benzene but instead it gives tertiary benzene. To prepare a pure sample of isobutyl benzene, the following procedure is used. With HI red phosphorus, aldehydes and ketones can be reduced to the corresponding hydrocarbon heating with HI and red phosphorus at 453 Kelvin. Bimolecular reduction. In presence of active metals such as magnesium, usually form of magnesium amalgam, aldehydes and ketones undergo bimolecular reduction to form symmetrical glycols generally called pinacols. The name pinacol was originally used for the glycol obtained from acetone, but now it is used as a generic name for all the symmetrical glycols. The reduction occurs by a radical mechanism as shown below. Disproportionation reactions. Disproportionation means self-oxidation reduction. An important disproportionation reaction of aldehydes and ketones is Cannizzaro reaction. Cannizzaro reaction. Aldehydes which do not contain an alpha hydrogen atom when treated with concentrated alkali solution undergo disproportionation self-oxidation reduction. As a result, one molecule of the aldehyde is reduced to the corresponding alcohol at the cost of the other, which is oxidized to the corresponding carboxylic acid. This reaction is called Cannizzaro reaction. For example, formaldehyde on treatment with concentrated NaOH solution gives methyl alcohol and sodium formate, whereas benzaldehyde gives benzyl alcohol and sodium benzoate. The reaction begins with the addition of an hydroxide ion to the aldehydes to form an anion Fi. This anion then transfers a hydroxide ion on the molecule of the aldehyde. The product thus undergo a proton exchange. Crossed Cannizzaro reaction. Like cross aldol condensation, cross take place between two different aldehydes to give all the possible products. However, is formaldehyde, the cross Cannizzaro reaction is of great synthetic utility since gives sodium formate and the alcohol corresponding to the other aldehyde. Intramolecular Cannizzaro reaction. All these reactions discussed above intermolecular Cannizzaro reaction take place between two molecules aldehydes. However, compounds such as Glycol which do not have contain two aldehyde groups can undergo intramolecular Cannizzaro reaction. Unsaturated aldehydes and ketone. Unsaturated aldehydes and ketone in which the carbon-carbon double bond is conjugated with the carbon-oxygen double bond are called alpha-beta unsaturated aldehydes and ketones. For example, structure of alpha-beta unsaturated aldehydes and ketones. The alpha-beta unsaturated aldehydes or ketones may be regarded as a resonance hybrid of the following three structures. The following points may be noted from the above structures. Although resonance structures I and third involve charging separation, yet their contribution towards the resonance hybrid is significant because the negative charge is located on the more electronegative oxygen atom, which can easily accommodate. The carbonyl carbon in structure second and the beta carbon atom in structure third carry positive charge. Therefore, these carbons will carry partial positive charge in the resonance hybrid as shown above. Due to the greater degree of charge separation, the dipole movement of alpha-beta unsaturated aldehydes and ketone is much higher than their corresponding saturated analogues. For example, methods of preparation. As already discussed, the most convenient method for the preparation of alpha-beta unsaturated aldehydes and ketones involves aldol condensation followed by dehydration and Galician reaction. Properties. Apart from the properties of individual functional groups, unsaturated compounds show some interesting properties which result from the conjugation of the two functional groups. These are discussed below. Electrophilic addition reaction. The characteristic reactions of carbon-carbon double bond are electrophilic addition reactions. However, in alpha-beta unsaturated aldehydes and ketones, the pi electron density in the double bond decreases due to electron withdrawing resonance effect of the C double bond O group, and hence alpha-beta unsaturated aldehydes and ketones are less reactive than simple alkenes towards electrophilic addition reactions. For example, electrophilic reagents such as Br2 halogen acids and persids slowly to the carbon-carbon double of alpha-beta unsaturated aldehydes and ketones than to simple alkenes. Nucleophilic addition reactions. We have discussed in this unit that the characteristic reactions of aldehydes and ketones are nucleophilic addition reactions. It is interesting to note that almost all the nucleophilic reagents which add to the carbonyl group of simple aldehydes and ketones also add to the carbonyl group of alpha-beta unsaturated aldehydes and ketones. However, alpha-beta unsaturated carbonyl compounds have two electrophilic sites, the carbonyl carbon atom and the carbon beta to it. Therefore, nucleophilic addition reactions to alpha-beta unsaturated aldehydes and ketones can take place in the following two different ways. Direct addition. If the addition involves the attack of nucleophile at the carbonyl carbon similar to simple aldehydes and ketones, this mode of addition is small, or direct addition or 1,2 addition. For example, conjugate 1,4 addition. The resonance structures of alpha-beta unsaturated aldehydes and ketones reveal that beta carbon atom carries positive charge. If the attack of the nucleophile occurs at this beta carbon, a pi sigma bond is formed between the beta carbon and the nucleophile, and the pi electron of the double bond shift towards oxygen, leading to the formation of an enolate ion. The enolate ion then picks up a proton to form an enol. The enol thus formed undergo tautomerization to form the more stable catoate product. Thus, although the net result of this reaction is addition to carbon-carbon double bond, but the mechanism involves addition of two parts of the reagent at positions 1 and 4, and hence this mode of addition is called 1,4 addition. Since 1,4 positions are the two termini of conjugated system, therefore 1,4 addition reactions of carbonyl compounds are also called conjugated additions. The complete process of 1,4 addition may be shown as follows. Factors governing 1,2 versus 1,4 additions. A number of factors govern the direction of addition of nucleophiles to alpha-beta unsaturated aldehydes and ketones. Some of these are discussed below. Reactivity of the carbonyl group. Reactivity of the carbonyl group. Since aldehydes are much more reactive than ketones are towards nucleophiles, therefore majority of the addition reactions of alpha-beta unsaturated aldehydes are 1,2 addition reactions. For example, conversely, since ketones are less reactive than aldehydes, therefore majority of the addition reactions of ketones are 1,4 addition reactions. For example, reactivity of the reagent. Organolithium compounds, being more nucleophile, predominantly undergo 1,2 addition to alpha-beta unsaturated ketones, whereas Grignard reagents gives mainly 1,4 addition products. For example, steric hindrance. Steric hindrance at the carbonyl group favors 1,4 addition whereas steric hydrogens at 3 position favor 1,2 addition. For example, addition of acetoacetic ester carbonate to ethyl cinnamate. Addition of ethyl cyanoacetate to ethyl acrylate in presence of sodium ethoxide. Addition of nitromethane to acryl nitrile in presence of sodium ethoxide.